So we've reached our last section in Chapter 8, and this topic is called improper integrals. So up until now, if we have been looking at an integral, we've been working with integrals of functions that are continuous, and if we look at a definite integral, we only look at it over a closed interval. But sometimes we need to find integrals for functions where the limits are infinite, and these are called improper integrals. Let me give you a picture of this. I think that'll make a little more sense. Think about this function, y equals 1 over x squared. So if we graph this, you'll notice that we have a vertical asymptote on the y-axis and a horizontal asymptote along the x-axis. And so you notice as the function decreases and as x goes out to infinity, it never touches the horizontal asymptote. So we would say any area underneath here, if we look at the area from 1 up to however high we go, we're never going to have a bounded region or a closed region. And that's what we mean by an improper integral. What if we were asked to evaluate the integral of this function from 1 to b? So now I'm just calling it b. B is just a generic variable. It represents some generic x value. So for example, if b were at 3, we would say the integral from 1 to 3. That would be area under the curve from 1 to 3. But I'm just saying b for any general number. So remember the fundamental theorem, we would find the antiderivative, which would be negative 1 over x using a power rule. And then we would evaluate it at the upper limit minus the lower limit. So that would be negative 1 over b minus a negative 1, so plus 1. So the area under this curve from 1 to some number b would be recognized by this expression. As b goes to infinity, however, this is an unbounded region because there's never going to be a place where this area closes off. It's going to be open the entire time. So if we were asked to integrate this function from 1 to infinity, one way we could think of this is to think of it as a limit. So what we could think of this as is the limit as b approaches infinity of the integral from 1 to b again. So we are using b as a generic number so that we can evaluate the evaluate the definite integral. And then what we're going to do is we're going to think of it as the limit as b approaches infinity. So in other words, if we were to keep looking at areas under the curve from 1 to b, what would those areas be approaching as b goes out to infinity? So the integral of this, we just said it was negative 1 over b plus 1 from back here. So now take the limit of this expression as b approaches infinity. Well, what happens to this first expression as b gets large? Negative 1 over b approaches 0, and so that just leaves us with 1. So the areas, this is what you want to think about, the area under this curve from 1 to different numbers, 1 to 2, 1 to 5, 1 to 100, 1 to 1,000,000. Those areas, as b approaches infinity, as b gets larger, are getting closer and closer to a value of 1 each time. And so we would say that the area or the limit approaches 1, so the area converges to 1. So let me formalize this a little bit. So as long as f is a continuous function on an interval from a out to infinity, then if we need to evaluate the integral of the function from a to infinity, this is called an improper integral, we're going to replace that infinity at the top with b, and we're going to take the limit as b approaches infinity after we've evaluated this integral using the fundamental theorem of calculus. We could also go to negative infinity. So if we were asked to integrate the function from negative infinity up to b, it would be the same idea. Now notice I'm using a for the lower limit this time. It doesn't really matter what you call the variable, but this would be equivalent to the limit as a approaches negative infinity of the function from a to b. We could also integrate from negative infinity to infinity as long as there's no breaks in the graph, and we would write this as the sum of the two separate integrals from from definition 1 and 2. So we would say it's the integral from negative infinity up to c, and we would evaluate it using this definition here, plus the integral from c to infinity, and we would evaluate this integral using this definition up here. So we would have to do it as two separate improper integrals. In the first two cases, as long as we get a limit for this expression, like in that last example, remember we took the limit, we got 1. As long as that limit exists, we say that the improper integral converges. So those areas under the curve as b goes to infinity, or as a goes to negative infinity for the other direction, as long as those areas are approaching a number, that means we're getting a limit for this definition, and that's what we say the area converges, or the improper integral converges. If that limit does not exist, then we say the improper integral diverges. In that third case, where we have the double integral, we have 2 of them together, if the integral on the left, or I'm sorry, the integral over here, we say diverges if either of these integrals diverges. And we'll do some examples here. So let's try this. We have the improper integral of the function 1 to x from 1 to infinity. So I'm going to write this as the limit from, as b approaches infinity, of the function, the integral of the function from 1 to b, because we want to work with b and treat it like a number. So ask yourself, what is the antiderivative of 1 over x? And of course, that's the natural log of x. We're going to evaluate it from 1 to b using the fundamental theorem of calculus. So that would be the natural log of b minus the natural log of 1. Of course, the natural log of 1 is 0. So this just gives us the natural log of b. And then we want to take the limit as b approaches infinity. Well, think about what happens here. As b gets larger, this also just gets larger. The natural log function is just going to get bigger and bigger as b goes out to infinity. And so we would say that limit is infinity. Well, does the limit exist? No, not really. So we would say that the improper integral diverges. And if you look at a picture of this, I want you to kind of see what's going on here. So we have the original function, remember, was 1 over x. So here's the graph of 1 over x. We were looking at the function from 1 out to infinity. So the idea is that if I were to think about areas under this curve from 1 to, say, 100, 1 to 1,000, 1 to 10,000, 1 to 1,000,000, those numbers just keep getting bigger and bigger and bigger and bigger. They never converge to a specific number. So the areas never converge, and we would say that this is infinite area. It's an unbounded region. And therefore, the improper integral diverges. How about this function? We have the integral from 1 to infinity of 1 minus x times e to the negative x dx. So we're going to rewrite it as the integral from 1 to b. So I'm going to replace that upper limit with b and take the limit as b goes to infinity. This is going to require integration by parts because we're multiplying 2 functions together. Think about your choice of u and your choice of dv using the Lippitt rule. I'm going to put 1 over x because that's the polynomial function in the u column, and then e to the negative x in the dv column. So we're going to differentiate the first column and integrate the left column, the second column. And so right here we've got, I've got plus minus, I'm going down the diagonal and then across. So that gives me negative e to the negative x times 1 minus x minus the integral of e to the negative x. Make sure you see why that's negative, because I had a negative times a negative and then a negative minus again. So it's still negative. And so e to the negative x, we can just integrate. Think of it like a little mini u substitution. And so if we put all this together, notice that these, what I did here algebraically, I distributed this negative e to the negative x, and I got this expression here. So notice these two e to the negative x's cancel out, and I'm just left with this expression right here. Now remember, we were looking at the integral from 1 to b. So fundamental theorem, because of this negative exponent, I wrote the value at the upper limit as b over e to the b. Make sure you see what I'm doing. Wherever there's an x, I'm replacing that with a b, minus the value with replacing x with a 1. So I have 1 e to the negative first, which is 1 over e. Now think about what's going on here. What's going to happen to this expression as b approaches infinity? Well, remember we talked about growth rates in the previous part of this chapter. So, of course, 1 over e is a constant, so we don't worry about that. But the b over e to the b, think about which of these grows faster, or grows larger faster, I guess I should say. So is it going to be the exponential function e to the b, or is it going to be just the b? Well, if b approaches infinity, e to the b is exponential. Remember, exponential, of course, far outweighs or outpaces the polynomial. So this denominator is going to get larger faster, which means this whole fraction is going to go to 0 and just leave me with, oh, here, actually, I broke it down using L'Hopital's rule here, which you could do. Limit of b over e to the b would be infinity over infinity. Take the derivative of 1 over e to the b, which would be 0. Either way you want to think about this, you can use L'Hopital's rule, or you can just think about growth rates. But make sure you see this first expression goes to 0 as b approaches infinity, which means that we are left with, where is it? Negative 1 over e. Remember, that was the other part of that expression. So our limit is negative 1 over e. So we would say that the integral, the improper integral that we were interested in, converges to the value negative 1 over e. And here's a picture of what this function looks like. It's kind of an interesting function. It's in the fourth quadrant here. And so as x goes out to infinity, even though there's an asymptote at the x-axis, as x goes out to infinity, the areas, if we keep taking areas from 1 to 10, 1 to 100, 1 to 1,000, whatever, those areas we're going to keep on calculating, are going to approach a value of negative 1 over e. And it's negative. I guess maybe I should use the word area. I should say the integral. It's negative because we're evaluating an integral, but it's negative also because it's underneath the x-axis. And so that's why those numbers are negative. But the point is those values are approaching, of each of those numbers as x goes out to infinity, are approaching a number. And that number that those values are approaching is negative 1 over e. Let's try this one. So we have the integral from negative infinity to infinity of the function e to the x over 1 plus e to the 2x. So here's what this graph looks like. It's kind of an interesting function. It looks almost like a bell-shaped curve as you zoom in close to the origin here. Because this is that third part of the definition from earlier, from negative infinity to infinity, we're going to break it up into two parts. So let me just back up really quick. I want you to see where I'm getting this from. When I say break it into two parts, sorry, let me go back. Here it is. This is what I was talking about. So this, in case 3, negative infinity to infinity, we break it up at a spot somewhere in the middle that kind of makes sense. The choice for c can be anything, but a lot of times 0 is a good choice because it's right in the middle of the number line. So I'm going to break this up from negative infinity to c as one integral, and then from that same c to infinity. Let me show you what I'm talking about here with this example. And where is it? Here it is. So where would be a natural breaking point? 0, a lot of times, like I said, is a natural breaking point because it's right in the middle of the number line, right? From negative infinity to infinity, 0 is in the middle. So I'm going to break this up as the integral from negative infinity to 0 plus the integral from 0 to infinity. And then we're going to look at each of these separately. So the first part, I'm going to write this as the limit as b approaches negative infinity. And I really glossed over some details here. This, if we did a u substitution, you would see this is the arctangent of e to the x. So I'm skipping the details on how I'm getting this antiderivative, but the antiderivative of this function, take my word for it for now. We can go over this again in the office so you see it, but this is the arctan of e to the x. Actually, if you pause the video and work this out, this isn't that bad. This is a u substitution. If you let u equal e to the x, the derivative, of course, is e to the x, and you'll see this is fits your arctan rule. In any case, we've got the antiderivative is arctan e to the x. And so for the first part, we're taking the limit as b approaches negative infinity from b to 0. You'll notice I switched to b here instead of a. The variable you're using to replace those infinities does not matter. It can be b, it can be a, it can be c. It doesn't matter. I kind of get in the habit of using b for all of them. But just so you see what I did here, I replaced this lower limit with b instead of negative infinity. And then remember from the definition, we take the limit as b approaches negative infinity of the antiderivative from b to 0, because 0 was my breaking point. And then separately, we're going to evaluate the limit as b approaches infinity. Again, I'm using b, call it a, it doesn't matter. But this b is the replacement for this upper limit of infinity from 0 to b. So let's look at these separately. So applying the fundamental theorem of calculus, the arctan of e to the 0 power, e to the 0 is 1. The arctan of 1 is pi over 4. That's where this number is coming from. Minus the antiderivative at the lower limit, which is b. So that's arctan of e to the b. And we're going to take the limit as b approaches negative infinity. And I would advise you, I didn't do this in the PowerPoint, but I would advise you to just work these separately. So like finish this limit, get that value, and then finish this other limit separately. I did them at the same time though in the PowerPoint. Over here I've got the limit as b approaches infinity of arctan of e to the b, so that's the value at the upper limit using the fundamental theorem, minus arctan of e to the 0 again, which is pi over 4, because e to the 0 is 1, arctangent of 1 is pi over 4. All right, so let's think about each of these separately. Now the arctangent function, that is probably not one you may recognize right off the bat, so I think I have a picture of it on the next PowerPoint, or the next slide here, so I'll show you what this looks like. Here it is. This is the arctangent function. So here's what I want you to think about, okay? Let's go back. We know this integral, or this antiderivative, we want the limit as b approaches negative infinity. So as b approaches negative infinity, e to the negative b does what? So think about smaller and smaller values as b goes out to negative infinity. What happens here? Oh, here it is again. Okay, so what happens here as b approaches negative infinity for this arctangent function? Well, okay, so as we go out to negative infinity, notice what's happening to arctangent. It's approaching 0. So arctangent of, it doesn't really matter that it's e to the b. It's arctangent as x or b goes out to negative infinity. These values are for the limit here approach 0. So that's this 0 right here. So this first expression becomes pi over 4 minus 0. How about in the other direction? As b goes to positive infinity, what does arctangent do? Well, go out in this direction. As we go out, as x approaches positive infinity, we approach a horizontal asymptote in the arctangent function, and that asymptote is at pi over 2. That's this number right here. So what do we have? We have pi over 4 minus 0 from this first integral, plus the limit over here is pi over 2 minus pi over 4. So that, of course, just leaves us with pi over 2. So we would say that the integral, the original improper integral, converges to pi over 2. Let me go back so you can see it. This improper integral converges to pi over 2. So the areas, if we keep taking bigger and bigger areas, as x goes out to negative infinity and then again to positive infinity, those areas will approach a limiting value of pi over 2.
Okay, I'm going to skip down to example 7 in the PowerPoint. There's one more example I want to go over with you. So we have the integral from 1 to infinity of the function 1 over x to the p, where p is a number greater than 0. So notice it's just a generic function, 1 over x raised to some power. Let's take a look at what happens in this case. So we are going to rewrite it first as the limit, or first I rewrote it as x to the negative p, just so we can work with it a little easier using power rule. Then we're going to write it as the limit as b goes to infinity of x to the negative p, the integral of x to the negative p from 1 to b. And so think about what would the antiderivative of this if p is a number. We would add 1, just basic power rule, add 1 and put that expression in the denominator. So we would have x to the negative p plus 1 all over negative p plus 1 from 1 to b. And so using the fundamental theorem, we would write that, remember, replacing x with b, so that would be b to the negative p plus 1 over negative p plus 1 minus the lower limit, 1 to the negative p plus 1 over negative p plus 1. And I want you to think about what would happen here as b gets larger and larger. What would happen in this case? Well, it really depends on the p value, right? Because if p is a number that's smaller than 1, right, then what happens here? So if p is a number that's smaller than 1, then this expression will get bigger and bigger as b goes to infinity. And so in that case, we would say this diverges. On the other hand, if p is a number that's larger than 1, and think about where I'm getting this from. I want to make sure we're clear on this. And we can talk about this again in the office tomorrow. But here's the idea. If p is a number less than 1, think about what happens right here to this exponent. So let's say p is 1/2. We would have negative 1/2 plus 1, which would give us positive 1/2. So that would leave us with a positive exponent. And so as b gets larger and larger, this would just grow and become a bigger and bigger number. And that would cause it to diverge. On the other hand, if p is a number that's greater than 1, so for example, let's say p is 2. We would have negative 2 plus 1, which is a negative exponent. So if p is a negative exponent, that forces this to move to the denominator. And so as b gets larger and larger, this expression would approach 0. That's what this says right here. B to the negative p plus 1 would approach 0, leaving us with the remaining expression over here, and we would say that the integral converges. We're going to see that again in chapter 9. That's a really important expression that's going to come up again when we talk about series, and so that's why I wanted to make sure we had that one.